Hello again. This is Roger Koch Barr for the Bioelectricity course. This is week 4, lecture 10. I thought in this point of talking about the Hodgkin and Huxley model, you were probably becoming exasperated and saying, well, if this model is so good, can't you show us just a few results? So let me do that. If we use the Hodgkin and Huxley model for active tissue and compute just 3 quantities, let's look at what happens. Here is the curve in this particular example for Vm. What happens to the conductances GNA and GK? Here is GNA. It rises rapidly. You notice that the time course of its rise is very similar to the time course of the upstroke of the action potential. These are both going up at pretty much the same time. GK is this curve. GK rises more slowly, crosses over right along about here. GK grows higher than GNA. If you take these curves as a whole, Vm, GNA, there, Vm, here, you can say, well, look, what's happening here is the following thing. Vm goes up because GNA goes up. GNA goes up, Vm goes up. Vm goes down because GK comes up. If we do it diagrammatically, sort of drawing ourselves a few pictures, let's look at that process again as we understand it by looking at these numerical results. We start off with our membrane patch. Our patch is just sitting there. Sodium ions are out here. Potassium ions are in here. Vm, potential relative to baseline, is equal to 0. So we're just trundling along here on the baseline. Vm equals 0. Very peaceful. Then a little bump comes along in Vm. Something happens to perturb Vm upwards, like that. So Vm is just sort of bumped up. And the consequence of that bump up, here's our membrane, here's Vm. Comes along, bumps up. And as a result, what happens? The sodium ions, which are outside, they all start going inside. Because all of a sudden the sodium conductivity increases. Sodium that had been held outside the membrane is allowed in. Because sodium is coming in, it's bringing charges with it. And Vm is going up, 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 up. Because all those charges are coming inside. Potassium, on the other hand, is just sitting here. A little bit further down the line, what happens? Here's our membrane. We've had a nice time. Vm has gone way up. Now, all of a sudden, the membrane diminishes its conductivity to sodium, finding it harder to get through now. But on the other hand, it increases its conductivity to potassium. Potassium starts going out. As potassium goes out, it leaves the interior as left more negative. And what happens but the action potential comes back down again. So this is the potassium current flow. So if we make some notes there, we'd say Vm at rest is just nothing much is moving either way. When it goes up, that's sodium coming in. When it goes down, that's potassium going out. Now when you go back, look at our curves. You'd say, well, actually, all this is not quite so cleanly divided into phases. Sodium goes up. Yes, it does. It goes up right there. But it still is elevated over here. Likewise, potassium is higher than sodium over there, but it's still pretty much increased over there. So there's not this clean-cut division that I have described. The division I described is a simplification. And as a result, you can't take it for being more absolute than it is. But on the other hand, it does present the main picture. Thank you for watching, and we'll talk some more in the next segment.